Oh yeah, it was crazy.
Oh my god. Well, hey, at least you can get crushed by drywall. That's bad.
No.
Yeah, that would be bad.
Almost.
That would be bad. You could probably punch your way out, though.
I don't know, that drywall.
Is that not
it was
the
like
case?
it was a 5/8 inch thick drywall, so
It's pretty thick.
yeah.
Drywall's tough.
Yeah.
Oh my god.
Oh, yes.
Oh,
So it's
People
different
think
hue.
it's down drywall.
Yeah,
So,
I saw some photos.
It was interesting because you get to some parts and you're like, oh yeah, and the whole wall would just like come off. And then there's obviously like the flood damage. So then there were parts you're like taking off like piece by piece. You're just like, but it was really cool. So
Were you in full suits, like hazmat suits?
only if you were doing sanitation. If you were there for
Yeah, the mold was
mucking
probably.
that, then you're just ripping everything out. You're like taking all the moldy furniture, putting it on the side of the road. You're taking all the drywall, putting it on the side of the road. You're taking out floorboards, putting it on the side of the road. And then if you're sanitizing, then you go in with all of your cleaning supplies and you scrub every single step. I was never on that team. I was always the mucking guy, so I didn't get to clean everything. I just broke stuff.
That's pretty
So-
cathartic.
Yeah, you can do a lot with crowbar. I've learned.
Crowbar's a good tool.
Yeah.
I like my crowbar.
It's a fun time.
It is. So friends, we had a break. I'm sure everyone knows that. You know, we're all back, more or less. So we had left off with an assignment, right? Some bifurcation stuff. Do you want to talk about any of that?
Yes.
Yes. Okay, good. I've got new stuff to talk about, but I want to talk about this till we're happy. I don't even remember exactly what problems I assigned. I've got some here. I don't think I gave all of these. Somebody help me out. Where are we starting? What are we talking about? So far, it's pretty easy for me. There's 4 problems, is that right? 5 problems. Can we write them up? Could somebody tell me what they were?
You had to make a face portrait for the first 2.
Oh, okay, cool. So what was that?
It's that equals sin x.
Oh, okay. Oh, right. So that's kind of one of the easier ones. So, okay, so these first 2 are phase portrait.
Mm-hmm.
And then what was the second one?
E to the x minus x squared plus 1.
Oh, that one I made up. What was number 3? Then these were do the bifurcation diagrams.
Yeah.
Okay. What was the first one, please?
That one is r plus. I
We're
just
good.
hit it.
Yes. Oops. Okay, please go on. Please do go on.
R plus x minus e to the x.
Oh, okay, cool. And then,
Rx plus x squared, x cubed.
and then Rx minus X cubed?
No.
X plus tan h Rx.
Okay, right. All right. So how about these first 2? Sketch the face portrait of those. So that is the line, right? So we're looking for a flow and a line for each of those 2. Just a single line, that's all we want with dots and arrows. Do we want to talk about those? Like, you'll have to tell me. I'm not going to try to read your minds. So Thomas is like saying yes, right?
Sure.
Yeah, good. Thank you, Thomas. I have a feeling everyone should be shaking their heads, probably. So, all right, let's do a different one than that. Let's say I had x dot equals cosine of 2x. Cosine of 3x. What the hell? Let's make things crazy. sketch the face portrait. So first thing I do is I literally just plot that like it's y equals cosine of 3x. Sorry. No, you always have to do it. You're always there helping me out.
Sometimes I forget that.
No, it's okay. It's really, you know, it's not, you don't have to feel like it's your job. But I wanted to make sure you felt that way today. So, first thing I would do is sketch this like it was y equals cos 3x, except I have x dot and x. So what is the period on this thing? See people tracing out coses, and that's good. What's the period on this sucker? Yes, what was that formula?
Oh my gosh. 2 pi over t or something like that.
Yeah, that's pretty good. It's definitely just like, it'd be 2 pi over 3 for this one. Is that what you said?
Yeah, okay.
Yeah,
So
2 pi over 3. So look.
Wouldn't 3 be the frequency? Or
Yes, 3 over 2 pi is the frequency.
Yeah.
Yeah,
Wait,
yeah,
Okay.
yeah, yeah. Period, frequency is 1 over period.
Yeah, okay.
Yeah, yeah. So I mean, here, look, think about this. You know, what would this, what's the period of this? 2 pi. I mean, I hope we all have a sense of what the period of that is. So that the period of normal cos is 2 pi. So you think, okay, so one period runs from 0 to 2 pi. So when cos is eating a 0, it starts a period. When cos eats a 2 pi, it's ending a period. So what if 3x equaled that and 3x equaled that? Well, then x equals 0 would be my start, and x equals 2 pi over 3 would be the end of a period. So you don't have to necessarily know any formulas if you just kind of reason it through. So that means this one's got twice pi over 30. I'm trying to get a good roll there, didn't get it. And then we just got a little cos in between there, and it doesn't have to be accurate. That's good, right? Because this one's pretty lousy. Cookie cutter, right? So now I know, oh man, that's bad. That's 2 pi over 3, and then, what's this right here?
4 pi over 3.
Thank you, 4 pi over 3, and then, what's that? Thanks, I'm just trying to wake everybody up a little bit. Seems like we might be sleepy. So, we got that going on there. And that means x dot is equal to 0 at these intersections. And x dot is positive in this region, so the increase would be to the right, or the change would be to the right. It would be an increase in x. X dot is negative here, x dot is positive here, negative, positive, blah, blah, blah. So I just extract the information that I want into the flow, and I've got, let's see, let's make this 0, then this would be a quarter of that, right? So let's see, what is 2 pi over 3 times a quarter, because this is the halfway mark right here, right? So that's pi over 3, so that's pi over 6, right there. So pi over 6, and I'm gonna put open circles until I think about the stability, and then negative pi over 6. And then we're cooking. So then negative 2 pi over 3. Yours is so much easier than this. I'm trying to like take a brutal one here for my own work. So between these two that straddle 0, we flow to the right, and then the flow alternates all the way through here. And then I consider stability. I hope, did I ask about that? Like classify, I guess I did, but not precisely, is that correct? I didn't say like address the stability, or did I? Well, let's do that. Let's address the stability. So in those first two, sketch the face portrait and at least just color the dots the right way, right? So we're gonna make a stable dot solid. No, we're gonna make a solid dot stable, is what I mean, and this is unstable. So I go through, let's see, this one is stable, unstable, stable, and then they alternate, right? So it's a very nice, pretty little, yes. Did I do something
Is
wrong?
there a, wait, is it at 2 pi over 3, negative 2 pi over 3? Is that where the dot's at?
Yes, sir.
Is it, I thought it was a little bit before.
Well, there's this one. So there's this one here, which is at negative pi over 6.
Yeah, so then one of the other one be at, like, because isn't negative 2 pi over 3, isn't that, it's not touching the line at that moment, is it?
It's crossing the axis
Is,
there.
oh, okay.
Yeah. So explain a little more about what you're thinking, Chris, because I want to get
Well-
to the root of what you're
Well,
asking.
I'm looking at it and the dot, like where negative 2 pi over 3 is, there's no dot on that.
Oh, well, I was just circling the
Ah,
intersections,
got it.
not like,
Okay.
yeah.
That makes more sense.
Okay, cool. I'm glad we talked about that. That should be a solid dot if I was,
Yes.
yes, and then an open solid.
Got it.
So that's pretty easy, right? Like this is pretty straightforward if you understand what's happening. If you don't, we should talk about it now. Yes, Hans.
So building off that question, why, if it's not intersecting with the x-axis, why do we have a dot at negative 2 pi over 3?
No, it is intersecting. I'm just circling the intersections.
Okay.
Yeah. It is touching it, yes. And then I was just circling it so that I wasn't like making any presumptions about stability. So that in that first one up there, I just circled where where x dot was 0. And then in this one, I did the coloring for stability.
Okay.
Does that make sense?
Sort of.
Well, what does, so we,
I guess if the cosine starts at 1 and a full period is 2 pi over 3, 2 pi over 3 it's not an x-intersect, is it?
oh shit, I see
Yeah,
what you're
that's-
saying.
that's what
Oh,
I
I
was
see
getting
what you're
at.
saying. It's labeled wrong.
Yes.
It's fucking labeled wrong.
Because shouldn't that be like
Oh,
pi
no,
over,
no, actually, this,
shouldn't
you're
it be
right.
like pi over 2?
Thank you. Yes, yes, I got it. Now I understand your question. Great question, because this is fucked up. That's what you were both asking. I see now. So this, yes, thank you. So that is so wrong. Yes.
It'd be pi over 2 and then negative pi
Yes,
over 2,
thank
right?
you.
Okay.
Why did I give myself a hard one? I'm clearly not ready for it. So each of these little humps is a pi over 3, right? So between any two dots is pi over 3 because it's half the period. So this is pi over 6 plus pi over 3, which is pi over 2, like Chris said. Yes. Thank you both very much.
Mm-hmm.
And then this would be negative pi halves. And then adding pi over 3. Yours isn't this complicated. Yours is so much nicer than this. Very, very happy. Great questions. Thank you so much. Other questions? And then, so this one is same thing, right? But I would get Desmos out for this. Like you probably would have trouble sketching this on your own. But same thing here. This one probably only has one.
Yeah.
Yeah, this one should only have one fixed point. Cool. All right, we good on that? And then, should we talk about these? Yeah, okay, cool, there we go. Oh, I just need a head nod. Just need a wee nod. Okay. So, for these, especially for, I mean, kind of for all of them, but for this one, I would definitely get Desmos out. And one thing you can do is, let's actually do something like this together. So I highly recommend doing this with a graphing aid because otherwise, you might do some shit like I did over there. So, oh, it's all ready. It's actually turned on and logged in and just lovely. So, I'll show you how to do this. And I think once you see this, it'll become really nice. I'm gonna do it. You're off today. Oh. Well, I won't do any of the ones that I'm asking from you, but I will do one like it. So let's say, well, let's just say we had x dot equaled, let me actually think. I want one that kind of acts like that. So, okay, well, let's just do something simple for the time being, and I'll try to think of a better one. And I think we did this one. This was the supercritical pitchfork, but let's go through it again so you can see the reasoning process. And then we'll do something a little different. So, graph for me, there we go. All right, so I'm gonna say y equals, and then I would literally enter the r. So you type in r, and it says, well, it should
When you're
say,
finished, it will.
it will after I keep going. R. Oh, okay, there we go. You don't have to type times either, that's good shit. So add a slider, wonderful, wunderbar, minus x cubed. Oh, I'll do a really good one. Okay, this just came to mind. This is exciting. This is super fucking exciting. So let's put a plus x to the 5th on there. This is pretty crazy. Yeah. Yeah, we're pouring the fire sauce on there. So cube plus x to the 5th. Oh yeah. Not the kind of thing you get graphed by hand easily. You could do it, you could use calc, but look at the subtle little changes in concavity. That would take a lot of work. That's a lot of hard calc 1 to get that all worked out. So this is for r equals 1, but I would start with a negative r. So notice here, now what I want you to watch is, and I would do this like first, I wouldn't start writing stuff until I thought about it. So make your movie, and then start watching the intersections and how they change. And what we're looking for, all we care about are those intersections and their nature. So right now, let me just keep going. So what happens as I move R? No, so the intersections are way, it looks like they're kind of at -2 and 2 and 0. Notice that 0 is always an intersection. And that makes sense because when x equals 0, x dot is always 0. So 0 is always a fixed point in this one. Not so much here. This one definitely has 0 as a fixed point all the way through. So I've got those two fixed points at -2, 0, and 2, but the ones on the outside, do you see how they're moving in towards 0? Now let's talk for a second. Is this stable or unstable? What's the flow to, is the flow unstable, right? Because the graph is underneath, so x dot is negative. So I've got an arrow pointing left here, arrow pointing to the right in that little bump, arrow pointing to the left here, arrow pointing that way. So unstable, stable, unstable. Does that make sense? Let's actually just kind of do the bifurcation diagram a little bit along the way. Just a loose one, so I'm doing a sloppy one right now. And I'm going to use solid for stable, dotted for unstable. So this was unstable, stable, unstable. So I've got like this, like here's, if this is 2, this is my R, and this is, say, -2 down here. Then I've got like this unstable branch that's getting closer, it's moving in towards 0, and I've got an unstable branch down here moving in. And in the middle, I've got a nice stable branch. Do you see how this is working? So what I'm kind of, you can think of this as a bunch of slices of this axis. So if you just took this and put dots on it, and then like looked at the movie slices of this, just where these intersections are, that's what I'm making over there. So let's keep going. So we keep moving, we get R, keep keeps going, and now something really, I wouldn't give you one like this, because this is really intense what's about to happen. Notice how there's two little bumps forming in the middle section. You see how it's starting to curve? And now watch, there it's perfectly flat, but look what, oh, look at that. Do you see what's happened there? Suddenly, two new equilibria sprouted out of the middle. Do you see that? Let's back up. Now we have 5 intersections, right? So these two just kind of came out of this middle one. 1, 2, 3, 4, 5. Watch how that happened. This scenario right here gave birth to 2 new ones. So they pop out of the middle. And I've got I would go in here and adjust the step size. I'm going to make a better step size because we want real precision here. Well, good luck. Did it even record that? Well, it did. Just doesn't seem very precise. But watch how they come out of the middle. You see, it's so hard, it's so damn hard to see that. But can you tell what I'm talking about? Is this making sense? Let me know if not. Okay. So these new ones are born out of the middle. Now this one is still unstable. The one on the right edge is still unstable. But what about these new ones that were born? What is their nature? Stable. What is the nature of the origin? Unstable. So at some parameter value, what was that parameter value? That was at 0. Notice that everything got weird at 0. Here, everything's cool, and then everything's basically this. So this keeps on persisting up until I get to r equals 0, at which point things get weird. This middle one splits off 2 unstable branches. Oh wait, no, or were they stable? Were they stable?
They're stable.
They're stable. So this one, it splits into 2 unstables, and then it itself becomes unstable. Now we keep moving. So let's get back in here and understand this a little bit more. So watch, born, and now what happens as I keep moving? Oh, what happened to them? Where did they go? They just disappear. So what happens here, and this takes a little bit of more timing, is you've got something like this. This is this thing is stable on the bottom, unstable on top, stable on the bottom, stable on top, unstable on the bottom. So we see a really crazy thing like that happening. And it's really weird. And I think that this actually doesn't have a cusp like that. I think this comes in and is like that. Isn't that wild? That is crazy shit. If this were a physical system, let me show you something really weird that's going on here. This exhibits, if this were a physical system, it exhibits what's called hysteresis. Hysteresis, which is not reversible. So this means if you've got some system and you've got a little control knob, and as you turn it, things change, but when you turn it back, things don't go back to the way they were. That is hysteresis. So this thing right here, if I'm changing R, let's say I'm on this, so I'm nice and stable. So I'm riding here, I get to the parameter value R here. And now, this is pretty crazy because if I keep going, I end up becoming unstable. So imagine there's a little noise. Like over here, because it's stable, if I'm off to the side, I always come back. But over here, if there's noise in the system, I don't come back. And right away, I would probably creep up to that thing there. And then, if I try to come back, I'm actually riding the top curve back as opposed to the bottom. You see that? It's like I move out this way, because I'm unstable, I leave the equilibrium I entered on at some point, and then when I turn the knob back, I'm actually in a completely different state than when I move to the right. I want to show you a really cool, I just learned this year, and I want to share this with you. This happens in all sorts of places, but I never knew it happened here. So let's see, man, woman, drawing, hysteresis. Oh, there we go. No, none of those. So check this out. Let's get that picture of here. All right, so now, this is weird. Sorry for the risqueness. So this is, as I write, so I look at this and I see like, I guess a quote, man, like a male-looking face, or just a face, right? Let's just say it's a face. And as I move this way, so here's the control knob, moving to the right, it's still a face. If I start here, it's still a face, and my mind locks onto that face and keeps imposing face upon this. Keeps imposing, and then here it starts to get weird, right? So it's an unstable. This is stable, becomes unstable. Here, it could go either way. But I'm still stuck on that face in my mind, so I see the face, and then all of a sudden it becomes not face-like at all. And I move over here, and I'm like, oh, it's that lady there. That sad lady, unfortunately. I guess, she looks like she's in mourning. But then as I come back, I can keep the women image. I can keep locked on it all the way until I get to here, and then it becomes unstable, and I snap back to the male face here, or the face. I'm sorry, I keep gendering things, but I'm an old dude, not trying. So I apologize. But this is an example of hysteresis in a place you would never expect it. And it's literally this bifurcation diagram going on. Here we are, face, 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 face. Oh, what is it? I don't know. Oh shit. Lady. 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 So whatever. Anyway, that's enough of that.
Actually, quick question.
Thank you. Thank you. Please.
So, on your diagram,
Wherever it was, yes.
Yes. When you drew the lines, you drew them straight. Does like the curvature matter when we're drawing our bifurcation?
Not for us at this early stage of it. It's really,
Just to show like that you know when it becomes stable and unstable.
Exactly, and the rough, like is it moving in? Are they becoming closer? Are they moving further apart? Just rough indications of that.
Cool.
Would be
Okay.
greatly appreciated. Thank you. You can literally get the exact curve. So check this out. If you set x equal to 0, x dot equal to 0, and you go to Desmos, and you say, plot this, where are all the r and x pairs where that equals 0? Let's go back to Desmos. So I'll just put a 0 here, and it will start, well, let's see, I'll change the r into a y, because I think it won't know what I'm talking about, unless I do. So this is now showing me the Rx pairs, and you can kind of see, is this going to work? I don't know if that's working. Oh, that's because I changed the text. Oh, it should be x times y. Oh, but yes, okay, geez. There we go. No? There we go. What do we got here? So, I don't know, maybe that's not that helpful. Yeah, maybe that's not all that helpful. But if you turn this to its side, you can kind of see that figure that I had with the line going down the middle, right? This looks like the bifurcation diagram with the line going down the middle. Let's do another one. Let's do one more that's weird. Let's do one like this. Actually, let's just do that one together. See what happens. We'll get you started on it. So we're going to do y equals, oh, how about this? Hyperbolic cotangent. I'll change it. Coth of Rx. There we go. Cool. Well, that's not good. Boy, I should, oh wait, there's more to it, isn't there? There was x plus, there we go. Okay. Beautiful. So now here, notice I've got two equilibria. So when R is super negative, I see two equilibria, and they stay fixed. Notice how they're not moving, really. But as soon as I hit negative 1.4, they start to move apart. Is the one on the left stable or unstable? Let me get back there. So is this intersection at negative 1, is this stable or unstable? Unstable, right? Because you've got negative flow, positive flow. And then you've got also the same thing. And the fact that I'm using it just screws things up because it blows up at 0. So I wonder if I can, no, let's just, change it to tan H, damn it. It's okay, you'll still have to put it together. It's so much easier than this one. So here we go. So I've got R is negative. I've got 3 equilibria. I've got an unstable, stable, unstable. As I move to the right, I notice that at negative 1, things change. So I'm making my bifurcation diagram. R, and then these are, you could label that like X star for fixed points. So let's see, so when R was negative and then all the way up to R equals 1, we had 3 equilibria. And we see that the outer ones are moving in towards 0. So that was an unstable on the other side, and a stable in the middle. Is that making sense? Let me know if this doesn't make sense, because that's really important, if this does or doesn't make sense to you. And then as I keep going, those actually get closer. You can see those getting closer there, and then suddenly the one in the middle becomes what? As these two disappear, what happens to the middle one? Unstable, becomes an unstable. What kind of bifurcation is that? Do you remember? That is a pitchfork, yeah. This is actually called a subcritical pitchfork because you're coming, the sexy bifurcation stuff's on the left. Underneath, it's sub the bifurcation value. Thomas, yes, sir.
So would that, on the diagram you do, like, would the intersection be at like -1? Or at
Oh, was it?
Yeah.
Was it -1? Did I say that
Yeah.
backwards? Thank you. Yes. Good call. How many folks actually got that one already done and did it right? Huh? Yeah. Cool. Good job. Does that help us on getting these done? Yeah? When would you like this due? I think I originally said start class Wednesday. Do we need more time on it? I'll take them up till Friday. How's that sound? Get them to but they have to be in my office by noon on Friday. Okay. Good stuff. I got a new story to tell you. We've got a lot of new stories to tell. In fact, the whole rest of the semester is a brand new story. I know. If you're a physicist, you've probably heard this story many times, or at least a couple of times. For some of you, this will be the first time you've heard this physics story. It's one of my favorite physics stories. Let's just make sure we got the appropriate pennage. Okay. So I am going to take a spring and attach it to a ceiling. I'm just going to let it hang. So now I've got a spring. Just hang it from the ceiling, no weights on it or anything, it's fully compressed. So let's say this is the spring. And springs are complicated things, but we're going to make it a simpler spring. So we're going to assume this is what's called a linear spring. I hate this one too. Please give me a better one. Oh, God. Okay, here's 2 more chances. And lotto. There we go. Hell yes. Okay. So this is called a linear spring. And what that means is that the force required, so if I want to extend it x units of length, the force required to extend it that x units is linearly related to the distance that I move it. So linear spring means this. And so this is extension. This is called the spring constant. So this determines, the larger this is, the stiffer the spring is. If you have a large spring constant, it takes a lot of force to move it a little bit of distance. So this is spring constant. And then this is the force. You could think of this 2 ways. Force required to extend x units, extend or compress x units. And you could also think of it as the force exerted by the spring itself, right? So you've got this kind of 2 things. Like if the spring is lifting something and it's pulling down, the spring is pulling back up. So it's all that weird physics shit that is helpful for physics things. This is called Hooke's law. Most springs are not linear. Most springs are non-linear. But we can always assume that if x is a small amount, this works. So even if you don't have a linear spring, which you probably don't, for small perturbations of x, we can assume this holds true. Think of it as you linearized it, and you got the linear approximation. So we got linear spring, Hooke's law. Okay, so now we understand that. Now we're going to put a mass on it. And you might want to do these drawings right next to each other. So now I'm going to attach a mass, and it's going to pull down on the spring a certain amount. So let's call this first distance here. This is just the L. That's the spring length. I'll move that across. If I attach this mass, it's going to pull the spring down, let's say S units. That's the stretch. Here's the length of the spring. Here's the stretch created by attaching the mass. And we'll just assume that goes right to the center of mass there, like so. What are the forces at action here? What's happening here? What forces are acting?
Gravity.
Thank you. Look at physicists. Giving bug-eyed looks to physicists. So that is pulling, that gravity is acting on that with a force of mass times gravity, right? We have Newton's second law, which says that if I have an acceleration acting on an object of mass m, this is the force that is produced, or required, I mean, and if I put this force on that object of mass m, it accelerates by this amount. So we've got these 2 things going on here. So this is just the force of gravity. What's the lay term for that? What's the lay term for your mass times the gravitational constant? What do you call it? Just weight. Yeah, that's just your weight, right? Like you have this specific mass, but we have if you're doing your mass in I guess the KGS system, right? That's meters per second squared, or in the English units, 32 feet per second squared. Multiply that times your mass, you get your weight. There's some subtleties here with units. You got to get all your units lined up. What is the other force? So the spring force, yeah. So the spring force is pulling back, and this isn't moving. We're assuming this thing has come to rest. So I have the spring force acting up. So we have mg pulling down, we have ks, the stretch, the extension on the spring pulling up. So at this moment, at equilibrium, we have ks equals mg. Spring force matches gravitational force. But that would be boring, because right now we just have a thing staying still. So I'm going to imagine we're already in motion. I've either taken this mass and like pulled it down or pushed it up, and then maybe given it some initial velocity in either direction too. So like pull it down and then shove it down. All sorts of possibilities how to get this thing moving. But we're going to assume now that the spring is in motion. So let's see here. So here's just the spring. Here's the spring and mass. And then here's the spring, mass spring in motion. So that means, let's look at it in an extension. It's where we've actually come down a little bit. So there's mass M. Let's label some things we know here. That was the original length of the spring. This was the equilibrium stretching. That's what it stretched. And now we've got a new thing going on here. We're going to call that X. So the change away from this equilibrium position is going to be X. X is positive if we're extended down. X is negative if we're compressed up. So let's mark this off here. So this is X positive, that's extension. X equals 0 is equilibrium. And X less than 0 is compression. And S can't be more than S, because S is like, you can't push past the natural length of this spring, unless you're shoving it up into the wood or something weird like that. So here's our scenario. All right, Newton, help me out. So this thing's in motion. We want to figure out how much force is acting here. So hold on, let me get, so the force is what? Let's think of the total forces on this thing before we do anything else. So what forces are acting on this now? There's a low-hanging fruit one. Gravity. That sounded very uncertain. You almost like tried to not say gravity again. So yes, so gravity. So we've still got gravity, right? That's right. Gravity's still pulling down on it. And it's acting in the direction of positive X. So it's acting in favor of extension. So we're just going to put mg here. But the spring is pulling back at the same time. So while gravity's pulling down, the spring is trying to pull it back up. So the spring is acting opposite the motion, right? The spring, if I'm moving up, the spring is pushing down. If I'm moving down, the spring is pulling up. Spring's always pushing in the opposite direction of where we're at, which we're moving. So here, we're going to say minus. So gravity works with the mass, and the spring works against. And I hope that when I'm done with this story, you could tell this story. So the force on the spring is going to be K, the spring constant, times the extension. Well, our extension is going to be the S plus the X now. That's the full extension. The equilibrium extension plus the X. Notice that if X is negative, then it shrinks this distance a little bit. So if X is negative, we're up past S, then we've shrunk it a little bit. Let me know if this makes sense, and if not, we'll talk. I mean, we're not all physicists in here, but we're math people, and as math people, knowing some physics is a damn good thing. All right, so that's the total forces, so F total on the system. That means it's going to result in an acceleration. So m times acceleration, this is the acceleration of the mass, is equal to these forces. X equals the position, or displacement. What's x dot at time t? This is x of t, yeah? What's x dot represent? Velocity. What does x double dot represent? Acceleration. So I can replace this a, because I'm trying to bring everything back to the system, I'm modeling. I can bring this a and replace it with an x dot. So a is equal to x double dot. That's the second derivative of x with respect to time. So we have m x double dot equals mg minus ks plus x. Awesome. Let's do some more simplification. So we've got mx double dot. Let's simplify this right side. Let's expand it. Do you see anything awesome that could be done there? Ooh, I'll get some tea while you think about that. Can I make that look better? The answer is yes. The question is, how do I make that look better and why? And look at these nasty constants. These are constants, right? These are just constants. What can I do with those? Do you know? Thomas, do you know?
I don't know. Or make it into this, can you just make it into like one constant?
Yes, and that constant's going to be 0. Why is that equal to 0? Why is mg minus ks equal to 0?
Because ks is equal to mg.
There we go. Yeah, it got a little deleted. Yeah, but at equilibrium, we already knew that ks is equal to mg, so these quantities just cancel. And we're left with mx double dot equals negative kx, and that we're going to rewrite as a one-sided equation. And we now have a model of the motion of a mass spring system. If we could solve that, we can't yet, but we will be. By the end of the week, we're going to be able to freaking solve that. If we could solve this, we'd know how to calculate the position of the mass in the spring at any instant. But what I really wanted to emphasize here is the thought process. Notice how we didn't think about the solution, we thought about change. Everything we did was thinking about rates of change in relation to position and all that stuff. This is how a physicist or a chemist or an economist, this is how scientists use differential equations to think. You think in diff EQ, then you solve it, and you've got a formula that you can give to, you know, a freshman or something like that, or an engineer. You can give it to an engineer. They can use that formula for you. I want to tweak that just a little. Actually, I want to say two things. So first off, this doesn't have any initial conditions, but if it did, if I had an x at 0 and an x dot at 0, this would be the initial displacement. So if I, pulled it down before I released it, that would be this, or if I compressed it a little, and this would be what? Initial velocity. So that's the part where I might not even move it. I might just take it and just shove it up, right? Like just give it an impetus to move up and down without any displacement. I want to do one more thing. This is fairly unrealistic because there's no entropy. There's no decay, there's no loss of energy here. That's not the way the world works, unfortunately. That's why we all freaking get old and die. That's why everything changes, right? Because everything is moving toward more disorder. Things are losing energy. So what we could imagine is that we had a vat here of some maybe water or something, or some kind of goo or some shit like that. There's shit. It literally could be a vat of shit. It'd have to have a pretty strong spring, but that could work. So we could have damping. We could have a damped spring, and that's the equivalent of friction. And then we can see a loss of energy. So I might also have friction in this force thing. So let's just add that in. So once we do this, we'll never have to do it again. And trust me, we're gonna spend a lot of time with that equation. So I wanna make sure we understand what's going on. If friction was involved, friction would be fighting this total force. Friction always works against the motion, right? It's always slowing you down, no matter what you're doing. If X is extending down this way, friction's trying to keep it from doing that. So we could add in here a term, and I'm going to use mu for now because I don't know. Isn't that a friction constant? Yeah, okay. So we've got a constant of friction. So friction constant. Coefficient of friction is probably a cooler way to say it.
That's what it's called.
Yeah, coefficient of friction. And friction relates to the velocity. Let's think about why. Imagine yourself in a swimming pool. You're out at a big public pool, or maybe you have nice private, maybe you have a private pool. I think it's sweet. Can we come over? And you're up to your chest in water. Just do this thought experiment with me because you've done it. You walk very slowly, and it's really easy, right? Like you just walk. You can feel the water, but the walk. What happens when you try to go faster? You feel it more. It pushes against you more. So the faster I try to go, the more it's pushing against me. I'm feeling more friction force from the water. So we're going to say that that is proportional to velocity. So friction is directly proportional to velocity. There, I get to use that symbol for today, so that's cool too. So if I put that in, how would this change this equation? Well, none of this stuff would change, but I would add this over. So if it is damped, so this is undamped. If it is damped, we now have an extra term, and we get mx double dot plus friction x dot plus kx spring force equals 0. Now we have 3 terms in there. And we could, these initial conditions can fit either of these just fine. So what would I even expect? What would I expect in a mass spring system with no damping? So now let's go to x versus t. Here's some initial displacement. If I put this x here and put a dot, that means I've extended the spring down. Because this is extension, right? So it's kind of weird. It's upside down from what you'd think. This is extension. I pull it down 1 meter, and then I release it. And if there's no friction, it just starts oscillating and never ends. So I have this harmonic motion, never losing energy whatsoever. What happens if there's damping? What does the picture look like with damping? Yeah. Right? It's going to lose energy. And over time, the vibrations, the oscillations are going to become, so I still displace it, but now there's a damping fluid. And then I did mean for that to keep on forever and ever, and not get closer and closer and shit like that. But I see it die out. If it's super damped, if I literally did put it in that vat of shit that I was speaking of, it would probably just slowly go down to equilibrium. So that's another possibility. There's like a couple middle possibilities in there. We'll get to them soon enough. Any questions on this? Because this is my key thing. I've got a little more to tell you today, but this is mostly what I wanted to tell you. So we're good on this? Do you think you could do this? I bet you could if you practice this. I'm not going to ask you to, but you hopefully could kind of piece this together on your own. That equation up there is just a small sliver of the whole types of equations we're going to be solving. This equation up here is, both of these are called linear homogeneous differential equations. So each of these are, or is, I don't know who gives a shit, is an example of a linear homogeneous differential equation. That word is homogeneous, this word is differential, that word is linear. Anything else? And then I'm going to put here of second order. So the order is just the highest derivative. Remember that? We talked about that. I just want to refresh your memory on that. So highest derivative level is 2. This is second order. Homogeneous means there's a 0 on the right side. When it's not homogeneous, just to like put this in your mind so that when you see it, it's not crazy. When it's not homogeneous, we might have a forcing function here. And we might have like some external, imagine here's the mass spring system, but underneath it you've got a jet that periodically shoots air up at the mass. That could be this F of t exerting an external force onto the system. And then, like, we're going to be able to set up these things with crazy parameters and then just watch what happens. We're even going to be able to do lightning strikes that thing. In a sudden cataclysmic force, that's called a Dirac delta. That's like freaking lightning strikes. That's like hitting it with an infinity for an instant. And that's going to be cool. That's going to be like the last part of the semester. So this part here is what I want to talk about for the rest of the hour. What does linear mean? Does probably you know, can anybody like, I just would be curious, what is linear? What does it mean to say linear?
It's changing x and changing y is occurring at the same rate. Like, if x changes 1, y changes 1, like it's a linear.
No, that's close, but it doesn't have to be a 1-to-1, but that's definitely, yeah.
Constant rate of change?
Constant rate of change, yeah. So like, let's go back to what Chris was saying with y and x. So what is the equation of a line, right? It's this, right, if we have that. That's not necessarily the same as linear. So what we were getting at here is this constant multiple of. So this operation here, just multiplying by a number, that is linear. But what makes it linear? So you're right, it is constant multiple. Like, and we're going to look at some fancier examples. But what makes it linear? And I'll tell you now, so you don't have to suffer hoping, like waiting for me to wait for you and not wanting to say anything. Let's not play that game. Let's see what I did have. Let's see what past me had to say about this. Not a lot. Oh, okay. Oh, wow. And I even have this up here. Cool. So let's just think by examples, and then we'll write out a summary. So suppose I've got a simple function of one variable, and it's f of x equals mx, constant multiple. And this f, I'm going to use some notation here so we don't confuse it with a couple of the other ones I'm going to write. So this means input is a single real number. Output a single real number. So you don't, no one would get the impression that that x was a vector or a matrix or something like that. A single real value. So that makes it really clear. Now what makes that linear is that it satisfies these two properties. Property 1. And so we base the whole idea of linearity off that simple example. If I take f of x plus y, so if I add the two numbers first, then push them into the function. So I take my inputs, add them, then figure out the output. It would look like that. And because of the distributive law, I can do that. And so that holds. If I add first, then apply the function, it's the same thing as applying the function, then adding. See how that works? So composition and addition kind of commute in a way. And then 2, if I take the argument and scale it, so this is just a constant. Good Lord. Constant. Then that would be m times alpha x, and because of commutativity and associativity, I can write this. And so that's just alpha m f of x. So I can pull scalars out in front. So that's the other important thing that signifies linearity. So if this is true, then the function is linear. These are your 2 main properties of linearity. So let's just take a quick look. Let's go back to this. Is that linear? Don't go too quick with the answer. Let's check together. So here's how you check. Is that equal to Kendra, you were making a head motion. What was your instinct?
Well, my first thought was it would be if b is 0.
Oh,
There's
what
no
a beautiful freaking answer. That's just like the best answer ever. Yeah, so this down here would equal mx plus b plus my plus b, and that would be, oh wait, sorry, got excited with that, a here. And then that would just be a times x plus y, but there'd be this damn 2b. And so Kintra noticed that, oh, this is equal to this if b is 0, right? So these two are equal, so we have equality only if b equals 0. In other words, i.e., this is the only linear function that looks like that. Even though the other one is a line, even though it's y equals mx plus b, it's not linear. Linearity doesn't mean I look like a line. Linearity means I look like a line and I possess the origin. That's linear. This, not linear. Line, but not linear. Very subtle. We're thinking of the relationship between input and output, and doesn't satisfy these properties. Let's take a look at another example. So what kind of time we got? Okay, we got 10 minutes, so I'm going to cut right to the chase here. Here's another example. Let's say D is an operator. Now that's a fancy function. An operator, instead of taking in real numbers, takes in functions and spits out new functions. So an operator, it eats functions and spits out functions. That's a whole different ballgame, right? So let's say D takes a function f and it spits out its derivative. So if I was thinking about, like, notice how over here when I wrote this to be really precise, let's be precise. So this D maps from differentiable functions. I have to be able to take the derivative of the input, right? Like the thing that I put in there, I need to have this exist. So it has to be differentiable. That means it's not going to have Sharpies in it. It's going to be smooth. So the input is smooth. That's differentiable. And it spits out a function that may or may not be differentiable. Doesn't necessarily have to be. So for example, if I were to take the function f of x equals x squared, if x is greater than or equal to 0, but negative x squared when x is less than 0, that function looks like this. So this is nice and differentiable. This is actually differentiable. Nice and smooth. And I can prove that. I don't want to get into it. But it looks like the tangent lines coalesce, right? Like there's no Sharpie. It doesn't look sharp the way I've drawn it. And that's not always an indicator, but if I take its derivative is going to be 2x when x is greater than or equal to 0, but negative 2x when x is less than 0. And that means the derivative looks like this. So 2x over here, super steep. Over here, negative super steep. Ouch. There's a sharp point at 0. There's this quick transition in the slope. This is continuous, but not differentiable. So that's, I just wanted to make that clear. But not differentiable at x equals 0. So just so we have a rough sense. Now let's forget about all that. But I wanted to at least mention it. So here, for example, I could take d of sine of x, and it would spit out cosine of x. It just says take the derivative, right? You can just read that as take the derivative of the thing inside here. But notice that if I take the derivative of f plus g, that is d dx of f of x plus g of x. You know, isn't this interesting? Here I'm suppressing the of x, but I'm putting it in out here because I know I got to do that, so I'm making it a little more explicit. I know it lives here, but I'm not thinking of those in that way. And then what's this derivative equal to? How would you do this derivative?
Derivative of f and the derivative.
Yeah, just the sum of the derivatives, right? Derivative of the sum of the derivatives. That's like one of your first things. You probably heard this in Calc 1. They said, oh, the derivative is linear. And you were like so freaked out about everything else that was going on, that didn't register. So this is d dx of f of x plus d dx of g of x. This is the derivative, d dx, is linear itself. It is a linear operator. I'm just hiding the fact that that's what we're doing by calling it d of. But d dx is linear. So this is just d of f plus d of g, and then really in a similar way, d of alpha times f, and this alpha is a constant, is equal to the derivative of alpha times f of x. And you know that when you have a constant, you can just, I mean, you've been differentiating a shitload this semester, right? Like literally like for 2 months you've been differentiating and integrating. More integration than differentiation. But I can pull that alpha out in front because the derivative is linear. So this is just alpha d of f. So to check linearity, you need to check these two properties holding for your thing. Let me give you one last example. Is there any, first off, any questions on any of that? No? Okay. Actually, 2 more quick examples, and then we'll call it. And I'm super glad we got through this today because you guys, I cannot wait. I'm so freaking stoked about what we're going to do. It's really one of the most beautiful, complete theories. You'll probably have the blessing to see in your careers, right? Like so much of this stuff is, so much of math and science is like, oh, I just know the tip of the iceberg. You're going to completely understand this theory by the end. You just own it. There's very few things in math you can really do that with. But these are anti-examples. Oh, well, not yet. Okay, so let's say I had d of f, and again, this is a differentiable function. And I multiplied it by x, and I took the derivative. So here I'm using slightly different notation. I better try to stay true. You can put the prime there, it's no big deal. Is this linear? So let's test it out. So I'm going to take d of f plus g. It's not super obvious when I look at it. So I'm replacing that f with f of x plus g of x. And so that's x of derivative of that, derivative of that. And so it looks like this thing is linear. Does that make sense? Check that out. And then similarly, I'm not going to do this because it's almost just boring. Similarly, d of alpha f is alpha d of f. So this is linear. Even though there's multiplication. Notice there's a multiplication in there, but that's still freaking linear in the way that we're understanding it. But here's the anti-example. I don't even know if that's a word, but I like it. This is, I guess, counterexample maybe is kind of the way. But let's say d of f equals f times the derivative of f. I mean, this multiplication worked just fine. You know, maybe this will work. Who knows? So let's try, I mean, we know because I said it's an anti-example. But so let's see here. So this is going to be f of x plus g of x times the derivative of f of x plus g of x equals f of x plus g of x times each, I'm going to use prime here because I'm getting a little tired of writing d dx. I'm kind of getting a little tired of writing in general. So we got that. Now I have to ask myself, is this equal to d of f plus d of g? And can you tell me, can you take a moment and tell me, is that the case? Are those two things the same? That's right, Kendra. You know, I'm always watching you, so if you ever want to answer something with just like little micro movements, I'll know you got it. I'm watching. Let's start cranking it through. Seems like there's a lot more shit up there, doesn't it? So how would you actually, you would have to FOIL those, right? You would have to FOIL this out. So this thing up here, after a proper FOIL, would look like this. I'm really getting sick of writing now. That did it. That just pushed me over the freaking edge. This has two extra terms in it that aren't here. So make sure you see that these two are not equal. So not the same. So this is not linear. So there's something very interesting going on about this multiplication versus that one. We'll talk more about that then on Wednesday. Thanks everybody. I owe you 30 seconds. Okay, I'll shut up.